Yeah.
I think recording has started. So let me just introduce once again. So we have Anubhav Chaturvedi, and he did his PhD at ICT with Professor Marcin Bałdowski, and now he is acting as an assistant professor at the University of Dansk. And today he will talk about characterizing quantum correlation using semi-definite programming. So please, Anubhav, you may start.
Um, Thank you so much, Neil, for letting me speak about one of my favorite topics. I'll complete my introduction here. I also, before starting out into quantum, I visited ISI and I worked with Manika and Somda there. And initially, Somda invited me to speak for a seminar on this topic, and I'd like to thank him as well. Um, it's a great day to talk about semi-definite programming. Every day is a great day. Um, Quantum theory is a semi-definite theory already. So we know that the density operators, the POVM elements, and even the maps are all have a semi-definite representation. In particular, the each any quantum map can be described by Krauss operators alternatively via the Jamakowski isomorph for Choi-Jamakowski isomorphism via density operators again, which are positive semi-definite. So the whole theory is positive semi-definite, and you can apply semi-definite programming across the field in a lot of places. There are a bunch of reviews that have now been uploaded to archive. One by Piotr Mironovich, which I subscribe to, and the other a good one by Armin, and there is one by Paul Skripchik as well. And those are they cover the expanse of applications of semi-definite programming in modern quantum information theory, which we all and the trust me, if you haven't checked it out, it's a lot of applications because the theory is semi-definite uh, positive is a theory of semi-definite positive matrices. Um, but here, I would say I am more interested in, let's just say, in the modern times, we'll say more interested in physics uh, and in especially physics in the sense that dealing with experimental observations. So experimental observations that I'm concerned with are generally between spatially separated parties, which might either be communicating or not communicating. And I call all of them correlations. So these are really talking
Anubhav,
about core. Yes.
sorry, are you changing your slides?
No, no, not yet. I'm
Okay,
just
okay, perfect,
talking about.
perfect. No problem.
Let me be precise. So before even starting this slide, I'm talking about why semi-definite programming is an important tool for all of quantum theory because quantum theory is semi-definite. Uh, and then I'm talking about why this particular sessions will be about applications of semi-definite programming, which are physical. And by physical, I mean that has to do with experimental behavior, which I refer to as correlations in this session. So today I'll be looking at it. So I think this is a particular physics application, and we'll be focusing on it. And specifically, we wanna characterize what kind of experimental behavior we can get from quantum theory. Okay, so characterizing quantum correlations using semi-definite programming as our favorite tool. So I have given a bunch of introductory lessons on semi-definite programming, but today I was amongst people that I have worked with, so I had to put in some things new. One of the details about semi-definite programming that I used to skip earlier was to do with duality. So I have made this introduction about duality, and we'll see how we use different aspects of the semi-definite programming duality um, here and maybe in more in the next session. But okay, semi-definite program is a semi-definite programming problem is an optimization problem. So you want to maximize or minimize something, take the supremum of or infimum of some quantity. That quantity has to be linear, that quantity has to be linear on some semi-definite objects, uh, which could be linearly constrained as well. So formally, we say here a linear function is optimized over a convex domain consisting of basically the cone of positive semi-definite matrices. And you're allowed to take intersections, or you're allowed to search over subsets of this cone, um, or subspaces of these cones, which can be formed of by taking intersections with hyperplanes, which are linear and half spaces. This is the formal definition. Um, the semi-definite programming general problem has a canonical form. Um, when stated in its primal canonical form, it can be thought of as maximization over some semi-definite positive operator x, uh, and what we are maximizing is a linear functional of x. So here it's like a generalized inner product between some coefficient matrix times x, okay, such that some linear constraints are satisfied. Here there are linear equalities, but we can include linear inequalities as well, um, via a technique called slack variables. But in general, all linear constraints are okay. What are linear constraints here? Again, some coefficient matrix like the C, or a bunch of them indexed by I times X. The inner product should be, so the inner product is basically mapping of mapping from two matrices now to a single number, which is in the case of constraint, it's bi. So, and the I index goes over all constraints, all such different constraints. um, while the important thing is semi-definite programs can be formulated in the primal as well as the dual canonical form. The dual canonical form changes the problem. So now you're no longer looking for a positive semi-definite operator, but for a real vector y, such that the constraint is semi-definite here. So, and this is the standard way of changing a primal problem to a dual problem. The constraint, the right hand side of the constraint, the bi, they now are mapped to the objective function of the dual problem, whereas while um, the coefficients of the constraint ai are retained on the same side of in the constraint of the dual problem. So they are the same, but there a summation appears, and the summation is with yi. Okay, and they must be semi-definite positive. There, if we subtract c from them, and the c comes from the objective function of the primal, and if we subtract it from them, the resultant matrix must be semi-definite positive. Oh, all right. So, what is the relation between these formalism? They happen to give bounds on each other. So that's the relation. Specifically, every feasible point of the dual SDP, it will return some value of the objective function by. So we are not looking at minimum, but just some solutions such that this constraints are satisfied. Then by will be an upper bound on the optimal value of the primal SDP. Okay. Um, And similarly, every um, every feasible point of the primal SDP returns a value of the primal objective function, which might not be maximum. If it is feasible, that means it satisfies the constraint, then it forms a lower bound on the dual SDP. Is that okay? In general, does everybody is are people familiar with the primal and dual formalisms of conic programs in general?
So we had two lectures last time, and there some sort of this discussions has happened. I think people will get it.
Oh, okay. This is cool. I hope it's also okay.
But please, you how you are describing, it's perfect. I mean, it's great. So you can discuss as details as possible. No problem. We have time.
Ah, okay. This relation of one program, one instance of the primal formulation of the program, program's feasible solution, lower bounding, the dual one, and the dual feasible solutions of the dual one, upper bounding the primal one. This is called weak duality. Okay. This is a property of semi-definite programs. If you can formulate the program in either one of the ways, then you get weak duality as a free um, uh, criterion. Um, Now we would like the bounds to be tight. No? If our semi-definite, if our optimization program is to be a good optimization program, it should return the exact optimal solution. So we get from big duality, we get a criteria for optimality, which is when uh, we have a feasible solution which returns the value of the primal objective function equal to a feasible solution of the dual problem, which gives the same value as the solution from the primal. So once we have that, we know we have solved the SDP because we know that is the optimal point. So our question is, can we turn weak duality into equality? That is strong duality. Now, it is good to ask this question because the SDPs are generalizations of a simpler class of conic programs called linear programs. And we are all familiar with linear programs. People looking into classical optimization or optimizations over classical theories or classical set of correlations typically end up with linear programs if they allow for shared randomness. But um, Right. But and LPs are always strongly dual. So their primal and their dual will always return the same ones, and the computer likes this, and it becomes easy. They are really easy to solve both analytically and computationally. SDPs are also efficient to solve, but we would like this property here. So, a sufficient condition for ensuring strong duality is that both are feasible. The primal and the dual SDPs are feasible. Then you get um, um, strong duality. And what else would we like to have for our SDPs? Um, when we use SDPs as a numerical optimization method, where we need that the optimal values of the primal and duals are attained. They are also feasible. So for strong duality, we only need some feasibility, but for but to solve it numerically, we want both primal and dual problem optimals to be feasible. That means in this case, there exists a finite positive semi-definite matrix X and a real vector Y, which yields the optimal values. Yeah. A sufficient condition for the existence of such coinciding solutions, the, of The SDP must be strictly feasible and its feasible region must be bounded. Okay. Um, and the equivalent thing is that both primal and dual problems are strictly feasible. Okay. Uh, and again, I will note the difference here. Um, for strong duality, we only require either the primal or the dual to be strictly feasible. If both are strictly feasible, then it's also numerically solvable. Okay. Let us take the simplest example, which is one of my favorite examples. It is that of state discrimination, and I leave it as an exercise to do it for any communication task. Okay, so this can be generalized to any linear functional, in not just the state discrimination test, and we can try it out and later. And if you like that way, then there is things we could discuss. But anyways, state discrimination or minimum error state discrimination, as it is stated in the form of a communication task, is a task where you have some set of states. I'm taking the simplest form, unbiased marginal, but in the simplest formulation, you have a set of states. Here I have used the symbol rho to denote density operators associated with the state, which are indexed by x, and x is a variable which we call as the sender's input or Alice's input, and x can take values in the alphabet capital X. The size of that alphabet is the number of different x's one has. So distinguishability of the maximum probability with which a receiver can guess what x is using a single POVM or a single measurement device without input is referred to as the success probability of state discrimination, or for short, I refer to it as distinguishability. Distinguishability is a characteristic property of the state, and it happens to form an SDP. Okay. Um, the maximum success probability could be written as um, uh, uh, so in the primal formalism of distinguishability with fixed states, the objective function is the success probability. So you have the uniform priors appearing outside. So 1 over the size of the alphabet, which is capital X, then summation over all values of X, and then you take basically the probabilities of obtaining the same outcome, or obtaining the correct outcome, which here turns out to be when the state is rho X, prepared by probability 1 over X, your POVM element marked by X is picked by the quantum measurement. So the POVM elements appear here. This problem is an SDP because the maximization, you can see everything else is fixed in the objective function except for the POVM. And because these objects are all positive semi-definite matrices with a linear constraint over them, that is the completeness. So they must sum up to identity, and they are positive semi-definite. So one might ask stupid question that why here only it's stated for a single x, but here it's stated for more than one positive semi-definite uh, uh, operators. Uh, uh, the reason for this is simple. You can always combine bunch of semi-definite positive uh, operators which do not feature in the objective function or in the constraint in products. So they are always they are only their tracial sums only linearly, they are only linearly combined. If that is so, we can always make another variable that is maybe the direct sum or some sort of combination of NKs. I am not sure, but I think, yeah, a direct sum would do fine in this case, and have this run on a single variable. That would be equivalent. But sorry for digressing. But anyways, I will just quickly recall the distinguishability um, is 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 the maximum guessing probability of the receiver guessing Alice's input, basically guessing probability of the input, and it's given by 1 over the probability of the alphabet appearing to the sender, x of x appearing to the sender. Um, and then summation over probability of success, or all the correct answers, which in this case is just answering the right input. So so there appears a sum over x and trace of rho x and x. When one observes the objective function, one quickly recognizes that this is an SDP because the operators nx here are the semi-definite positive variable. So if one uses the map from primal to dual, one ends up with a very simple dual formalism. Um, Here, there is a minimization over a semi-definite positive variable sigma. So you have trace of sigma, minimization of just trace of these observable, such that sigma minus rho x is always semi-definite positive for all x. Okay, so for state discrimination, this is the dual SDP. Okay? And here you see the dual is pretty insightful because it's simpler to gauge. And it is a good exercise for one to see how the primal yields the dual through the map. Okay, what is the utility of learning about primal and dual? I want to show you via an example. This is one of my favorite example. Let us consider a set of the simple set um, uh, of of 3 qubit preparations. Okay, the set has 3 qubits, and those are the trine states. Basically, those are states that are placed on the equilateral triangle on the Bloch sphere. So here's the Bloch representation. Um, um, so let us see what can we say about their distinguishability. Um, so we will consider dual first because it's very easy to work with the dual in this case, and in general also things become simpler. But it, when it comes to communication, that so we will consider a feasible solution. So we will consider a sigma, which is just identity on two-dimensional Hilbert space. Um, then it's easy to check. Now, rho x's are states. Their maximum eigenvalue can only be 1. And identity has the maximum eigenvalue, all eigenvalues 1. So we know that sigma upper bounds rho x for all x, just because rho x is a state. So this way, we get an upper bound on the primal objective function or the distinguishability. So it turns out the way to get it is max over nx, 1 over 3, um, sum over x, trace of rho x, and x. Now, if I replace sigma here, uh, sigma is identity, so it goes away. So I'm just left with nx, and then I can take the summation inside. So sum over x and x. So what we are left with is identity again, or sigma again, which has the trace of 2. So we get an upper bound 2 over 3. Okay, so I will point a quick mistake. In here, there should be 1 over x also appearing in front of the dual objective function. I think so. Yes, it seems
So,
so.
Anubhav,
Yes,
I have one just naive questions.
yes,
For example, if the states are not random, I mean, for example, row one, row two, row three,
yes,
if all the states are not coming with one-third
yes,
probability,
yes.
let's say if it's some, then also the sigma would be I by 2 identity.
Yes, you can actually write different operators here in the constraints. So let us take the operators to be subnormalized, okay, and then it's all fine. So if you take the state to be rho x times probability of x and write the primal problem, then the dual problem will appear in sigma is greater than equal to px times probability of x. So uh, instead of looking at and the solution will still be identity, but will be proportional to identity for sigma. But that's for later. But do you understand how one would capture non-uniform priors?
Exactly. Okay. Okay.
Do you get it? And in the same way, one could also generalize to arbitrary linear functionals also. And which I leave it, which I leave for people to try as an exercise. Once you do that, you will have a good grasp of primal dual conversion, which is very helpful. As by the end of this lecture, I will try to convince. But this is first part of convincing. Then we will move to a lot of theory recalling in different direction. But now what you have seen is the first statement of weak duality. I have a feasible sigma, so it satisfies all constraints of the dual problem. And so the bound on the objective function of the dual, which here should be corrected to 1 over x, uh, is 2 over 3. For this feasible one, the objective function is takes this value. This is then here is an upper bound on the objective function of the primary. Okay.
Uh, uh, Hi, Anubhav. Uh,
Hi, Ram.
can I ask you?
Yes, of
Just
course.
can I ask you one simple naive question, maybe little bit naive, but so if you just go back to the previous slides, there you are actually, if you look at the primal problem, it's like like the normal problem that we are trying to find out the operator which actually maximize the sum of the distinguishing probability, right?
Yes,
But if you look at the dual problem, you have specified that this is the dual problem, right? So I'm
yes,
saying let's take one simple example. Let's say I have only two states. Let's say they are row one and row two, and then we know that what are the optimal measurement on the block sphere to distinguish them, right?
yes.
But what will be the dual operator there? Means what is the physical significance of sigma in that case? Can you just elaborate on that?
Physical significance is something that I have been trying to figure out, but but it's better to see it in, I think, the conic program problem. So it returns a face which comes from above and really upper bounds your feasible primal space. So uh, that is, and I think it would be good to discuss for better interpretations. But in general, just like probabilities are to Bell inequalities, so you have that kind of a map. So instead of um, returning um, uh, as you can see here, it does not the primal program would return as optimal an x, which is a positive semi-definite matrix. Here it will only return uh, here it will return hyperplane
I see.
on some positive semi-definite cone.
I,
Here it's AI, which is defined by AI and CI. So it will select that one. So here trace of sigma appears, and that's the tricky bit. But I leave it for people who will try to map for all sigmas. Sigmas will always end up in or similar to the identity form. Now, considering state discrimination of uh, to uh, to pure qubits or to in general state discrimination of two qubits, the primal and the dual always coincide. And
I see.
uh, for for instance, let us consider this example because it's in front of me. I will look at pairwise, maybe if you say so. We could get back to this on the iPad later, but I have solved this one for you. Here also, the POVM. that the computer will return nx. Uh, it has a simple form. It's just 2/3 times your density operator for that state yields the exact value 2/3. So I have a feasible solution for the primer as well as the dual. So and they happen to give the same bound. So I know that the distinguishability of these states are 2/3. In general, yeah.
So means I'm saying in that example, like the dual, the sigma is also a positive operator, right? So what will be the solution of the dual if I solve it? Like you said for the primal problem, the solution will be two-third density matrix. Like the measurement should be the two-third row one, two-third row two, two-third row three. So what will be the solution for the sigma for in case of dual?
Identity over two.
It will be identity only. Yeah.
Yes.
Oh, I see. I see.
So
I see. Oh,
you see, because they are actually because the dual is actually just having modifying a real vector, and that in this case it will turn out to be a real number, I think so. But I'm not sure. Uh,
I see.
it relates to a very simple movement, which is beta times identity, basically. So so there is just one number that upper bounds all, and that number will be your um, upper bound on the guess lower yeah, the minimum of that number will be the lower bound upper bound on your guessing probability or distinguishability.
Okay.
I
Okay. Thank you.
All right, no problem. So we have strong duality in terms of state discrimination. Also, the generalization. We have strong duality for all such problems. So whenever we have a linear functionals of the POVM that is of this form, um, and linear constraints on the POVMs, you can have additional constraint other than completeness. Um, they are good problems because they are most likely to be strong. They satisfy strong duality, and also the criterion for numerical optimization. So typically such problems, if you give your computer, the computer is really good at it and will always solve the right solution or the best solution up to machine precision. So it's good for the computers. Shade discrimination. So before we move on, this brief introduction is for the idea of primal and dual, and we'll return to it if in the next session if you guys wanna see more of state discrimination communication. All right. So it, uh, when I started out, I learned I use semi-definite programming mostly in the context of Bell scenarios. This is the most popular context, um, and you guys must be familiar with Bell scenarios. So I'll quickly introduce the preliminaries of Bell scenario and uh, some 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 quick uh, some quick remarks of the different sets of correlations. So let us consider a bipartite Bell scenario where Alice has some input X and gives the output A, and Bob has some input Y and gives the outcome B. These are typically spatially separated labs where a source distributes some correlation to them. Uh, as a consequence of the experiment, um, uh, the parties they note the frequency statistics of how the outputs appear, and they take a log of this. Uh, and in infinite trials, it approximates uh, a conditional probability distribution. And this is one way of looking at it. The other way is that they share a resource that always produces the conditional probability distribution. So in such a Bell scenario, because of spatial separations, there are the linear no signaling conditions that all data must satisfy. These are zero measure conditions, so really no data ever satisfies them. But uh, when we look at it theoretically or in an ideal case, uh, the data should be such that Bob should not be able to infer the choice of X from his data, which his data is the choice of Y's and the output B's that he got. So choice of X should not influence these data. If the data changes, then you can deduct the presence of X. So that should not happen. These are linear constraints. So just using these constraints and positivity and completeness of conditional probabilities, all linear constraints, we get um, we get the set of allowed probabilities. They form a polytope. This polytope we refer to as the no signaling polytope. Whenever whenever your feasible region forms a polytope, um, which is a simplex, then you know that all because of the linear conditions, you know that all membership problems and characterization of this set or the boundaries of this set becomes LP. So it's very easy to do so. Um, Similarly, we have the non-resource set or the set of local causal correlations. So everybody knows local causality a la Bell. I'll just recall that probability distributions that are non-resource or local causal, they form a polytope as well. And my favorite way of describing, again, the hidden variable could take infinite values, but it's enough to take uh, as many hidden variable as the deterministic vertices of this smaller polytope. Um, and basically, the fact that local causal correlations are local hidden variable conditions are equivalent to no signaling plus deterministic correlation gives you a nice characterization of the local causal polytope. So the local causal polytope um, is a, is a subpolytope of the no signaling polytope, or the deterministic polytope is the subpolytope of the no signaling polytope, which has at its extremal point deterministic no signaling correlations. Okay? So all vertices of the local polytope also form uh, the vertices of the no signaling polytope. Again, very easy to characterize. Just to recall, characterization typically means things like membership problem and proving separation theorems. And a complete characterization of a polytope can be given again in two terms, which are dual of each other. One is by listing the deterministic extremal points, the other ones by listing the boundaries or in this case, this would be faces of the polytope. Okay? Those are hyperplanes on the space of probabilities. Um, uh, I gave an example of a deterministic vertex. Here, uh, Alice's outcome for the exit input is pre-decided. So if you change the outcome, you move around in the polynomial. Now, everybody is familiar with Bell inequalities. Also, Bell inequalities, the good ones are in general any hyperplane, basically any condition on the probabilities that allows you to exclude the local causal correlations, or the local causal correlations lie on one side of such a boundary is called a Bell inequality. But the good Bell inequalities are the ones that form facets of the local polytope because they are tight conditions for membership. But in general, there could be a more general criteria for good Bell inequalities that they should be linear on the probabilities. And here I present a general version of a Bell inequality where you have some bunch of arbitrary real coefficients C, X, Y, A, B, and typically you can always take them to be positive. So, which if you take them to be positive, you'll get a upper bound in terms of what local causal correlations can achieve. And this upper bound is given by beta L, and this should hold true for all local causal correlations. So if there is such an inequality, it's called a Bell inequality. And if a Bell inequality is non-trivial, if there exists some no signaling correlation, so in the no signaling polytope, but not in the local causal polytope, if there exists non-local correlations like this. If there exists any non-local correlation, then they must violate a Bell inequality. All of this can be very easily visualized from the polytope structure. And I give an example on the right hand side: local correlations, the facet, and and if the good Bell inequalities, linear facet Bell inequalities, and if there is a point outside, then there must be such a facet which will be violated by that point. And this provides a natural, natural to the local polytope criteria for non-locality, and also a measure. The violation of the Bell inequality then up to normalization can be looked at as a distance from the local polytope. So, mhm. um, so it gives a measure of non-locality. So Bell inequalities are really nice, and but we are done with characterizing classicality. Those are LPs, and people have done them over and over again. We are now interested in the more finer aspects, which is the boundary of nature's correlations or quantum correlations. So we must look at quantum strategies. A quantum strategy is can be thought in two ways. One is what the experimentalist does, which is we supply the as the rotations, we supply the experimentalist with a shared entangled state and ideal measurements. Uh, or in this case, I denote the shared state as rho AB and the measurements as MXA and NYB. And this is a strategy for the experimentalist to perform the experiment. And I can already know what, in ideal conditions, what the experimentalist would see. Um, this, but here we are using it in a different way, which is useful in cryptography. Here we are saying, okay, um, a behavior that the experimentalist sees is quantum if there exists such a state. So one is from the point of view what can be done in the experiment, and the other one is point of view what can be characterized via the experimental statistics. Um, and we are interested in this session, and we are interested in the maximum amount of non-locality on offer um, um, uh, with respect to violation of Bell inequality. So given a Bell inequality, how much violation I can get? And as I showed, that translates to a measure on non-locality. So we want to say we know that nature is non-local, and we were very excited about it. But now we want to ask how much non-locality is on offer, and we say quantum theory represents nature, so these are bounds on nature is bound on non-locality on offer. Um, if we consider the CSS, a slice of the CSSH polytope, so here the boundaries of the local set here are the CSSH inequality. Then and and the set Q is on a slice, it looks like this, is the quantum set. Then we know that there exists a unique point um, uh, called the Sirelson's point, or that maximally violates the CSSH inequality. It violates it all in the traditional form. It violates it all the way up to 2 root 2. But the form of my choice is in the CG notation. which is the minimal form of representing no signaling correlation to any well scenario that people have agreed upon, and it can essentially be translated to other forms. So it's 1 over root 2 minus 1 half. And then there is my other favorite one, the game form of CSSH. So here the Singleton bound appears as 2 plus root 2 over 4. Um, the SDPs, they like the CG or the traditional way of dealing with this is easy to communicate when we stick to the CG notation. It's the minimum. Okay, we know that the CSSH inequality, the no signaling bound is 4 and the classical bound is 2. So the quantum point rise eerily in somewhere in between, very mysteriously. All right. So as I told you, the main aim of SDP's application in that scenario is to characterize whether is to help us solve the question of membership, whether a P is realizable in quantum theory or not. Look, if a P is local, it's always quantum realizable. But in general, we can define the question whether a non-local P is quantum or not. This problem can be this problem is if you solve this problem for all P, then you also get a solution for another problem, which is equivalent, that find the maximum violation of a Bell inequality, of all Bell inequalities of a Bell inequality. So you consider not just the face set ones, but also tilted one. That way you can characterize each such thing. Um, they are equivalent. So we'll be focusing on the second version of this. Membership is a very useful for proof techniques. This is more useful for, in this case, bounding non-locality for on offer, the second formalism, where we are looking to maximize a linear functional of probabilities. That's it. The most general inequalities we can consider in such a way. And the objective function is just the CSSH in the CG form, because only the zero outcomes appear here. Rest of them can be generated by no signaling conditions. Um, Now, such that look, the state has to be positive semi-definite, and the measurement operators also have to be positive semi-definite. That's quantum theory. So it's essentially a three-tier SDP problem. But the problem is here that the objective function is not linear in the SDP variables, all of the SDP variables, but it has products of uh, the SDP variables. A and B are in tensor product and they're getting multiplied by the shared state. The constraints are linear on the respective semi-definite positive operators. If you just want to get a lower bound, if you just want to search from within quantum theory and get a lower bound on the maximum violation, the trick we typically use is that of the seesaw method. Here, we notice the fact that each separate tier of the semi-definite of this problem, which is not a semi-definite programming problem, forms a strongly dual semi-definite programming problem. So let's see what it means. Suppose that I fix the measurements of Alice and Bob to be some random allowed POVMs. Then the objective function now is a simple linear functional of the state, and a very simple linear with some very simple linear constraint. Such a problem is strongly dual and for finite Bell scenarios, and also for finite dimensional Hilbert spaces. The computer really likes it and can solve it to arbitrary precision. Um, so we take this optimal state and we use it as the constant in the next step, where we keep um, a one measurement operator, say B for Bob, or the one party's measurement operators for Bob as constant, and as the randomly initialized one, but row is the optimal one from the previous step. Now the new SDP becomes now the new optimization problem becomes an SDP on Alice's measurement operators. Again, the computer really likes it because the objective function is a simple linear functional of your POVM elements, and it always finds the nice solution. And so we then transfer these optimal measurements as constants in the next round and optimize over Bob's measurement. And in this way, we get really nice converging lower bounds. This strategy is very generically applicable and is a great tool. But um, but we are not but we are interested in really characterizing the boundary of quantum set because we realize the boundary of nature's non-locality or non-local correlations, and it gives us tests to falsify quantum theory. So we really want points on the boundary of the quantum set, and they happen to have really nice cryptographic properties. So they're they are useful in everyday foundations and cryptography. Maybe I'll speak about the cryptography part a bit later. To do this, uh, we rely on one of the most prominent tools for characterizing extremal quantum correlations, which is the NPA hierarchy. Um, as of today, there is just no problem in Bell scenarios that cannot be mapped to an NPA hierarchy-based approximation solution. However, it's a computational tool. Again, as the Bell scenario grows, uh, it becomes too hard to compute. Okay, the problem explodes and it's too hard to compute. There is problem the yeah, there is a paper by Peter Brown and the Fuzzy brothers that even maps uh, key rate of DIQKD protocols even in the non-IID scenario. So the essential question of device independent cryptography to an instance of a NPA hierarchy based problem. So uh, this is really the most uh, a tool that works across Bell scenarios and across protocols, and everything that is important can somehow be accessed or approximated through the NPA hierarchy. So up till now, I'm just motivating the word NPA hierarchy. What is it? It is a hierarchy of semi-definite programming relaxations of the quantum set. So essentially, a the quantum set's convex, but not a polytope, so it has infinite extremal point, and so it's hard to characterize. So the NPA hierarchy refers to an hierarchy of uh, convex sets uh, um, that contain the quantum set, and the hierarchy is labeled by a number, a very specific number for the level of the hierarchy. And as the number changes, goes higher, you get tighter and tighter approximations of quantum theory. And the best part about this application of NP hierarchy is that when you have really high levels of the hierarchy, you recover the quantum set. Okay? So it's a converging series of better approximations of the quantum uh, set. Um, why is it important? Because it gives a semi-definite programming realization, which our computers can then access. At the heart of NP hierarchy is an observation, or as I state here, a theorem. If I have a bunch of linear operators, then if I construct a matrix called the moment matrix tau, uh, which I will say is hinged on a positive semi-definite operator rho, um, then if the matrix has entries as defined here, the ijth entry of the matrix is just the moment of rho with respect to operator OI and a conjugate operator OJ, the conjugate of the operator rho J. So this quantity of this one entry is called a moment of the quantum state rho with respect to the operators O and OJ. This such an operator forms a gram matrix for pure state, and um, and hence it's always positive semi-definite. And if it is for pure states, then you can just mix them to create for any density operator. This should be positive semi-definite. And this is the main theorem that lies at the heart of NPA hierarchy. Now, by carefully constructing the set of operators, I can create moment matrices whose entries will now correspond to the probability distribution in the Bell experiment. And then I can ask the membership problem by constraining from the experiment the probabilities in the moment matrix, the entries of the moment matrix that correspond to probabilities, and I can ask whether such a positive semi-definite matrix exists. Okay, let us consider the first level. The for the CSSH scenario, the operator list only has 5 operators. So the first one, by convention, we keep identity. Uh, the second one is for Alice's first settings first projector, and then second settings first projector for Alice, and similarly Bob. Please excuse me for the tensor product structure. So and PA hierarchy does not see tensor products. It just sees operators and then commutation relations to enforce spatial construction. So it's the same hierarchy applies to Coach-Specker contextuality as well, because there are just commutation relations between observable. Um, so now, essentially, using this hierarchy, the 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 membership problem of the quantum set can be relaxed to an SDP. I'll show you in a bit later. Um,
Anubhav,
yes, yes.
yes. So I'm saying we are almost we have completed 1 hour. So I mean, it's up to you. Maybe you can stop at some point and continue the discussions for the next session. Anything.
Um, I'd like to finish. I'm sorry. I will
No
go
problem.
on speedily and quickly finish because I have this thing that I'd like to show you. So
Sure.
I will just move over the content um, um, quickly. Um, so what is meant by the level? The level refers to starting from O1. You have a string, you take the minimal operators because the other operators can be created with identity. O1 has additionally, so these are all, consider them as strings of length 1. Then a level L will have all operators made of the operators in O1, which have the length L. And for example, O2 will have operators of the form AA, BB, and AB. Okay? And it's a stricter approximation. This was the basic idea of moving. So I made a movement matrix for you guys from a pedagogical perspective. But basically, it's saying that if you construct such a movement matrix for the CSH scenario, for the level 1, you'll see 2 quantities that have no physical meaning, and they could take arbitrary values, and they're not constrained by um, anything from the experiment. So this is what the program essentially searches on. Um, and as you can see, there are some nice symmetries here, where the row corresponds to the diagonal elements, and the other probabilities are there in this square here. So just running this program, and it's very easy to run. You get for Q1, you get the Sirelsons found directly. So how do we prove this in Elson form? So if I have a quantum strategy from inside quantum theory, that means I'm going from inside quantum theory that reaches to root 2, and then I have even the level 1 of NPA hierarchy returning to root 2, then I know, because the sets of NPA sets contain the quantum set, then I know that this is maximal violation of uh, the CSSH inequality that can be attained in quantum theory. So either you have a strategy or you can find such a strategy via seesaw. So this is what this slide shows. Okay, so this was just pedagogical purposes, and I will quickly end with some of one of the most interesting things that I found regarding this. So this slide is to motivate the level of NPA hierarchy as a measure of complexity of characterizing extremal quantum correlations. Okay, this is the premise of this slide. Now, L is a good measure because it characterizes the size of the moment matrix already. So it's a good measure of complexity in terms of how fast my classical computer will run it. Um, and specifically, we are interested in the minimum L, which returns type bounds on Bell inequality. So I know quantum bound from quantum theory, or I have a guess for it, and the minimum level at which your NPA program attains this, we are considering that quantity, the minimum level, as, or we are proposing that quantity as a measure, a generic measure. Again, because NP hierarchy is generically applicable, um, at least theoretically, if not in practice, then this is also a generically applicable measure. Now I will recall something from the from a little bit outside. So some people might have heard of it. These are the sum of squares decomposition. So uh, if we find the quantum value, say beta q of a Bell inequality beta, and if we can find some polynomials in the measurement operators pi, such that this operator beta q times identity minus beta uh, admits a semi-definite positive decomposition, which means it can be written as a sum of pi dagger pi, which are, these things are always positive semi-definite. Then we say that we have found a sum of squares decomposition. It's another way of finding maximal violation, and it has nice consequences when it comes to self-testing or characterizing of quantum devices. So people might have heard of it. Now uh, it happens that the NPA hierarchy is and the SOS, finding an SOS decomposition, are primal dual problems of each other, and the level of the NPA hierarchy then corresponds to the degree or the minimum degree of the polynomial in a tight SOS decomposition. And this is to motivate that. I think if you guys have objections, say, but I think the level L tells us how easy an extremal point of quantum correlation is to characterize, or it's not, is difficult to characterize. The SOS connection has implications to self-testing, and we'll see. So this was the question when I started out, and for years I've been trying to. I had different answers for it. We are in the simplest scenario. We know that in I3322 we cannot have a finite level, but we know that in the CSSH scenario, a finite level L of the NPA hierarchy. We know that the NPA hierarchy does converge to the quantum set. We don't know whether it's a finite level or not, but the question is, at what level is or how complex is the CSSH scenario to characterize? Uh, by which we mean what minimum level of the NPA hierarchy is enough to characterize this level. This is the question. Quickly, does anybody of you have a pre-established a guess? Okay. So when I was at SN Bose, Manikda and people believe that um, a really low level should be enough, like 1 plus AB and so on and so forth. And one example of this is when we considered CSSH inequality that are tilted towards one single correlator. So you have the CSSH inequality here minus some tilting parameter times alpha. Okay, and we know its maximum quantum value and the classical bound, and we know that we can achieve this via level 1 plus AB because we have tight from Pironio and Bam's paper, we have tight SOS decomposition, and the polynomials are at most in degree 1 plus AB. So a very low level Q1 plus AB, just the Q1 operators plus AB operators is enough to characterize the tilted CSSH inequality. But the situation changes drastically. So we let us consider a doubly tilted CSSH inequality. And in this article on the right side, so the doubly tilted CSSH inequality has the CSSH inequality plus some tilting parameter alpha times Alice's correlator, marginal correlator, plus beta times Bob's correlator. The local bound can be found very easily to be 2 plus alpha plus beta, and the quantum bound was unknown. And in this paper, we solved this problem. We not only solve this problem, but we show something much more powerful, which is the self-testing statement. So we find a way of finding the maximum violation of the Bell inequality and also the optimal measurements and states that attain it, which are unique under local isometries. And they are given here and also in the paper. And we find that as alpha tends to, so we focus on the symmetric case where alpha equals to beta. And as alpha tends to the critical boundary, we require more partially entangled states. And and similarly, something similar happens in terms of measurement. So as for the CSSH, we require maximally incompatible measurement, but as we move towards the boundary, we require less and less compatible measurements. But then we tested what level of NPA. Now, having found the exact quantum value, we did this using Jordan's lemma, that is by going to qubits and solving this. So there was Jordan's lemma here because each party had two inputs and two outputs. So we can apply this lemma and find quantum maximum probabilities analytically. When we applied NPA hierarchy, we saw a very unusual phenomena that is exploding of minimum NPA levels in the simplest spell scenarios. We found all the way up to level 10 of the NPA hierarchy. We had to use an arbitrary precision solver for this. Was not enough to get the right value, which we found analytically. So in even in the simplest spell scenario, really high levels of NPA hierarchy are not enough to characterize the 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 extremal quantum correlations. I will stop here and maybe explain um, these results a little more in the beginning of the next section. But these are the most exciting things. But that's it. Thank you.
Thank you, Anubhav. Now we can take some questions. So if anyone can, anyone, if you have any questions, please unmute yourself and ask Anubhav directly. I don't know that. I think no one has any questions so far. Okay, Anubhav, thank you once again.
Thank you.
Then from here, probably will start the next session, right?
Yeah, yeah. Eh, I will not keep much content for the next session because I can't get the pacing right at the moment. But I will cover the last few things and then open for discussion so that we could all discuss potential things and stuff.
Okay.
But that's it.
Okay, Anubhav. Thank you. Thank you for your
No,
time. And yes,
thank you.
thanks a lot.
See
Okay,
you.
then we can end our call here
Yes,
today.
yes. Thanks, me. Bye.
Okay, thank you.